Hello everyone, my name is Tony, and in this video I'm gonna walk you through the MoveIt tutorials, but with a twist. Instead of using the default Franca Panda robot, we'll be using a universal robot manipulator with an OnRobot gripper instead. If you are watching this video, then I assume you already know that ROS, the robot operating system, is a very powerful and popular middleware to control robots. And within ROS, the MoveIt motion planning framework is the default and quite powerful motion planning framework used to control robotic manipulators. However, if this is your first time using MoveIt or ROS and you are going through the MoveIt tutorials, you will see that they use the Franca Panda robot as the default demonstration robot. So if you have a Franca Panda, then great, you can just follow through with the tutorials just fine. But if you have a different robot, then there are a few things that might be confusing. So this video is just that. I'm gonna go through the tutorials on the MoveIt website step by step. I'm gonna explain what I do at each step and how I adapt the tutorial to my robot. And hopefully you can watch this video and follow along if you have a similar robotic setup like I do. This video is not an explanation video of how MoveIt works. If you want to deeper dive into how MoveIt works, you can check it out on their documentation. There's also a bunch of walkthrough and tutorial videos on YouTube about MoveIt. There's this video that I really like from a channel called Mike Likes Robots, and I would actually recommend that you check it out first before watching my video. Alrighty, let's begin. So here we are on the MoveIt documentation homepage. I'm using Humble, but if you are on Jazzy, a lot of things will be the same, so it should be okay. So let's just click on tutorials, and as you can see, we have here 6 tutorials. So getting started, Quickstart, your first C++ MoveIt project, visualizing in RViz, planning around objects, and the pick and place tutorials with the MoveIt Task Constructor. So we're gonna actually go through all of them. For the getting started tutorials, it will walk you through installing ROS2 Cocon, and it will actually also clone the MoveIt tutorials package and install all these dependencies. So this will actually build MoveIt from source and build other MoveIt packages as well. Now, I don't actually recommend going through these steps because I assume you already have ROS installed. If you install the full desktop version of ROS, you would already have MoveIt in there. And also the MoveIt tutorials package include a bunch of examples for other robots as well, which we don't actually use for this video. So we will only install things as we go, only the necessary stuff. So we're gonna skip this, but instead I will walk you through this package. Let me zoom in as well. So this is for the robot that I'm using, which is a universal robot attached with an OnRobot gripper. Now, this is a package that I wrote that sort of helps you combine the URDF of the gripper and the robot. So it should work for any combinations of a universal robot E-series and an OnRobot gripper. So that would be a UR3e, UR5e, 10e, and the grippers are the RG2 or the RG6. I'm actually going to go through the installation steps of this package and just walk you through what we already have. Okay, so I have a fresh terminal here, and we're gonna first create a ROS2 workspace. So let's just call it MoveIt workspace, and then we have a source folder inside it. Okay, so let's go to our newly created MoveIt workspace. Here's source, and we are going to clone this repository. Here it is, and then we're gonna install the dependencies. So this package actually will install another package, which is the driver for the OnRobot gripper. So let's do that. Let it do its thing. Now it's done. Install these dependencies for Modbus. I've already got it installed, so it says already installed. And here's the important stuff, is to use ROSDEP to install any missing dependencies. So by this point, if you don't already have the driver for the UR robots or MoveIt or other things, it will install it here. In my case, I already have everything installed, so it doesn't do anything. All right, so let's just build our workspace. And we're done. And we can source it. All right. So in this tutorial, I won't be using a real robot, so we won't need to do any hardware setup. But what we can do is just to view the URDF. So there's this handy launch file that will let you set the UR type, so what robot you're working with. I'll be using UR3e, but if you're using UR5e, you replace it here. And my gripper is the RG2 gripper. So if you want to know what options are available, what you can do is, let's just have a look at this launch file. And you can add this at the end, so show show arguments, and it should tell you that for UR type we have all these options, and for the OnRobot gripper we have the RG2 and RG6 supported. So right now we'll be using the UR3e and the RG2 gripper. So when we launch that, RViz should pop up. So here's a robot, and you have the typical 6 degrees of freedom for the 6 joints of the manipulator, but also this finger width. We zoom in here. Yeah, so for the RG2 gripper, it goes from about 11 centimeters all the way to 0. Cool. So this is just to visualize the robot. We can turn that off. Now, what we'll do is we'll start the driver itself, but we'll be using this use fake hardware tag. Basically, what that does is whenever control commands we send to the robot, it will just assume that it will execute and go to that joint positions accordingly. Right? We're only doing a simulated robot, anyways. So that's what we're gonna do. So again, we're going to copy this here, and we're still using the UR3e and RG2 instead of robot IP because we're not connecting to a real robot. We will be setting this use fake hardware to true. That should pop up with another RViz terminal, RViz window, I mean, and this is our simulated robot now. So then let's just close that. We can now also start MoveIt. So this package already comes with the MoveIt config for this robot. So that's all we need to do. I'm gonna open up a new terminal, and since we're in a new terminal, I'm just gonna source again, and then I'm gonna start MoveIt. Alright, so that should pop up with another RViz window with the motion planning user interface already enabled. So here's our robot, and if you're using this package, then there are a few default configurations that you can make the robot go to. So this is basically this first tutorial, the Quickstart tutorial on the MoveIt documentation site. So here in this example, we're launching the Panda robot, and it walks you through importing the motion planning, visualization, and walk you through what each of these things do. Let's actually have a look to see if we can replicate everything that is here. So first, it asks us to play with the visualized robots. So the robot should have the robot visual, the planned path, the start state, and the goal state. Right. So our robots have exactly that. So if you open up the motion planning tab here, you can see the scene robot. So we turn that off, you can still see the orange bit. The orange one is actually the planning request. So here's the planning request where we're querying the goal state. So we can turn that off, and then we're only left with the model of the robot. Okay, and the start state is green. And right now the start of our path is the current configuration. Typically, that's what you want to do. You always want to start from the current configuration. So let's just query the goal state for now. And for the planned path, it will show the path once we've made a plan, as we will soon see. But there's a few options where you can loop it and show trail as well. So let's give it a go. So here we can move this gizmo around, as you can see. We can also rotate. There you go. And let's just say we want to make the robot go there. So all you need to do is hit plan. It will complete the plan. On the left here, if we click on show trail, we should see that we should see the entire plan like this, or we can just hit on loop animation to constantly see it as well. So that's the plan we're going for. Looks good. So let's execute it. So I'm going to hit execute, and our robot should follow. On the left here, for the goal state, if you click on this drop-down menu, there's a few configurations that is already defined in the SRDF of this robot, like the home position, the up position, which is what we start with, and this task configuration, which is like this, which is a pretty nice start for something like a pick and place task. So let's actually go there. We're gonna plan. Looks good. Execute. For this robot, the gripper is also actually a planning group. So in the planning group here, if we select the gripper instead, you can go to joints and set the finger width if you want. Or in planning, there's a few predefined positions that we've set in the SRDF, like opened, which is all the way opened. So we plan for that. This should be a simple opening motion, and we can execute. All right, let's switch back to the manipulator planning group. Let's see what else MoveIt suggests that we should try. So we've been doing this interaction. That's nice. We can check for collision as well. So let's have a look at that. If we move the robot into self collision, you can see one of the fingers of the gripper is touching the robot body, so it like highlights in red, like so. In the tutorial, it also tells us that we can enable collision aware IK. So if we enable that and we try the same motion, it should come up with a solution that, or it will try its best to come up with something that's not in collision, but sometimes it's just impossible. Okay. Planned. Oh, this one is 360 to reach there. Execute. Cool. Now, our robot, this is only a 6-degree film robot, so we can't actually try this out. And so here it's showing that this is this slider when you click on show trail that we can use. So let's give it a go. We just plan a trail here. All right, so that will be panel, which is planning trajectory slider panel right here. And we can walk through that trajectory step by step. We can also plan for Cartesian motion. So for example, if I want the robot to go sideways, like so, if we do a regular plan, like we hit plan here, and let's show the trail, you can see from the top that it does a sort of circular motion there. But if we want to force it to go in a straight line in Cartesian space, we can use Cartesian path here and then plan, and then let's show that. So only 10 waypoints, but it's definitely going in a straight line this time. We can execute. Very nice. Cool. And we can also change the velocity and acceleration scaling as mentioned here. So all these steps work just by using the default motion planning RViz tools and panels that is provided. So with any robot, once you set up a MoveIt config, you should be able to do a similar thing in RViz. But that's not very useful when you want the robot to do something dynamically. For example, combining it with perception and doing a pick and place task based on where the camera sees objects in the environment, something like that. For those other things, we need to dig into the C++ or Python API of MoveIt to write our own scripts to do something like that. But this RViz default motion planning panel is very useful just to test that you've set up your MoveIt correctly. Okay, so let's go ahead with the next tutorial, which is the first C++ MoveIt project. Okay. So firstly, what it asks us to do is to create a new package called Hello MoveIt that depends on these packages, MoveIt ROS Planning Interface and RCA-LCPP, with a node that's called Hello MoveIt as well. So let's do that. I'm actually going to leave these two running. Just going to close it down and open up a new terminal. And I'm going to go to our workspace that we created, the MoveIt workspace, and then into the source directory. And here we'll create that package. Now let's open up this hello MoveIt.cpp file in our favorite editor. Mine is VS Code, so I'm going to open that. Okay. So in source, as you can see, we've cloned the OnRobot package, and during the installation steps, we've also cloned these OnRobot packages. That gives us the robot. And here's the Hello MoveIt package that we just created. In its CMake list, it should have this Hello MoveIt node and should depend on the MoveIt ROS planning interface. Here's the package XML, which also says that it's dependent on this, which we will use. And in source, we can see the CPP file, which is just a empty default main for now. Okay, so here we'll create a ROS node and executor. So let's copy and paste that into here. Okay, now let's see if we can actually build and run it. So we're still gonna follow through the steps here. I won't be using this mixin debug tag. This is necessary in this tutorial because they're building the entire MoveIt Tutorials packages and MoveIt itself. So typically this would take a really long time. So that's why they use a debug mixin. We don't need to. So let's open up the terminal again. And we're going to go back to our workspace. And actually, before we do this code and build step, we are going to do a raw step. So here's a command for that, raw step install home paths source, ignore source. So this will find all the missing dependencies that are defined in all the packages package.xml file. So if this is your first time running this, potentially as defined in here, you won't have this MoveIt ROS planning interface package. So in that case, it will install it. For me, since I already have it, it should just say all required ROS steps installed successfully. So now we can build. So we're going to do colon build, and we are also going to do -- symlink install. So this will create a symbolic link to our launch files and other things. And let's just build. So it should build everything, including the Hello MoveIt package. It's building right now. Very nice, that finish. And obviously do not forget to source after you build. And now we can run this Hello MoveIt node. It should just run and exit without error, because the code is actually not doing anything except for creating a node called Hello MoveIt, create a ROS logger, and then just shut down. Nothing else. Okay, so let's move on to actually using the move group interface. So at the top in the include, we have already included the header, so we should be good to go. And we're just gonna copy and paste this code block here into this next step goes here spot. There's a few things that we need to modify here from the default code. So as you can see, it set the move group interface to find the Panda underscore arm group. Now, if you open up RViz again, you can see our group is called OnRobot manipulator. So we should be looking for that instead of the Panda arm. So let's change it. OnRobot manipulator. Like so. Make this slightly smaller. And our poses here might be reachable for a Panda, but we don't know whether it's reachable by the OnRobot or not. So we're just gonna go ahead and play this anyways, and it's very likely that with this default target pose, the planning will fail. What this code does is it creates this pose target as a geometry messages pose message with these values X, Y, Z, and the default orientation. So by default, in ROS, Z is the axis that points up. So if you set, and in this message, this is a quaternion. So if you set W to be 1, and assuming that X, Y, Z are all zeros, this is the default orientation, which is that Z up. And essentially, if you're trying to set this as the target for your manipulator, it will point your end effector to the sky. And typically that's quite a difficult pose to reach. So we'll see how well this goes. So after creating that pose target here, it will use this plan function that is inside the move group interface object and pass to it the plan message. And if everything is okay, so if it's a successful plan, it will also return the plan here. And in this code, all that we're doing is, if the plan was a success, execute. Executing is actually making your robot move according to the plan, or not, then we just pass planning fail. So let's just give this a go. So all we need to do is to build and then to run it. So let's do that. So here we're gonna build again. So let's see, we have that previous command, and I'm gonna add more tags here. So instead of building everything again, let's just build the package that we want. So we can do that by doing -- packages select, and we are only doing hello_MoveIt. Sweet. I am going to source again, and let's just run it. So before I run it, I will open up our RViz here. Let's put it to the side. And let's just see if this works or not. So ROS to run hello_MoveIt, hello_MoveIt. Oh, it actually worked. Very cool. So the plan was a success, so that's why it executed. So here you can see, as I mentioned before, we're pointing our end effector to the sky because we left it at the default orientation. And we look at the code. We're going to x is equals to 0.28, y is equals to negative 0.2, and z is 0.5, which is roughly what we see here. So this is negative. So this is our y-axis, and this is about negative 0.2 or 20 centimeters, and this is positive x, 0.28, so like 28 centimeters. And it should be around 50 centimeters from the bottom. All right, very good. So our hello MoveIt script works, but obviously there's a few things that can be improved here. In the code at the moment, if the plan is a success, which means that it can actually do the inverse kinematics and find a path that's not in collision with itself, then it would just execute, which is sometimes not what we want. Usually we would want to observe what that motion looks like before we make the robot do the motion. And maybe we would want some visualization debug messages in RViz as well, which is what this next tutorial is, visualizing in RViz. So let's do it. Here's visualizing in RViz. And so what it asks us to do is first to add this MoveIt visual tools to our dependencies. So let's copy that. And in our hello MoveIt package, we're going to go to package.xml, and we are going to add it here. Save. Also in our CMake list, we have to make sure that it can find it. So let's add it here. And add it as a dependency. Oh, thank you, Copilot. So we add it as a dependencies for our hello MoveIt node. Very cool. And in our CPP file, we're going to add the include. Now, if this is your first time doing this, your VS Code or whatever editor you use might flag it. Oh, sort of like this, right? So we'll need to install it first. We're going to go back to our terminals. And all we need to do is to use rosdep. So that's all we need to do. Do the rosdep command again. In my case, I've already installed it, but if you run this for the first time, you will see this MoveIt Visual Tools being installed. Now we can build. So we can do the same thing, just to see that we can build. We haven't made any changes to the actual body of the code yet. So this should build just fine if we install the right dependencies. Cool. Let's follow along. So now we need to create a ROS executor and spin the node on the thread. So let's follow with what it tells us to do. Firstly, we need to include thread. Just gonna add it at the very top. So our ROS logger is the same. We will need to spin this single thread executor up. So let's just copy that part. And we're just gonna put it under here. Like so. Yep, so that just spin up the single thread executor. And down at the very bottom, we need to make the thread joined before exiting the code. Cool. Now we need to create and initialize MoveIt Visual Tools. Here to create the move group interface that we have already done, and we construct and initialize MoveIt Visual Tools under it. So we're going to copy that. Just put it over here. Now MoveIt Visual Tools is setting the origin of all the visualization to be Panda link 0, which is the base link, the first link of that robot. So in our case, it should just be called base link. There you go. Right, so here are a few closures that it suggests that we use for visualizations. As written here, closures are function objects. It's a thing in C++ that have access to variables in our current scope, and it will be very useful. Each of these closures will just call a function on MoveIt Visual Tools, as mentioned here, and that is why we are passing it into these closures like that. So let's just copy that, and we're gonna create it here. So this one just draws a title, which is just a text that displays in RViz, and it's setting the translation from the origin, which is base link, by z in the z-axis by 1 meter. So for our robot, 1 meter might be a bit too high. So I'm gonna make it like 0.6, something like that. And here is using this publish text function to display a text. So this prompt function actually, as described here, it blocks your program until the user presses the next button in RViz. We'll talk about this next button later. But this is good for us to do like a step-by-step process, such as planning the trajectory, and then before executing it, visualizing it first. And if it does not look good, then we don't want to hit next to actually execute it. Here is a very useful one where it draws the planned trajectory toolpath. So different than the robot path or robot trajectory that we were looking at, this is only the toolpath, which is the end effect of it. And that may be very useful for us to track it before executing. So again, here by default using the Panda arm, so we're gonna change that to our move group, which is the OnRobot manipulator. Okay, cool. And let's just visualize the steps. As mentioned here, we're using the same target pose as before. And then instead of directly creating a plan for the target pose, we copy this chunk of code here and put it here. What it's doing is to prompt the user to press next and then draw this planning text, in our case 0.6 meters above the origin, and then do the planning step. So it won't plan until we press next, because prompt is a blocking function. Cool. And then instead of just executing the plan if it's a success, you can copy this code here. What it's doing is, if the plan is a success, then it will actually first draw the toolpath using that draw trajectory toolpath function. And then it will prompt the user again to press next to execute it. So we have a chance to have a look at the planned path before execution. And if it fails, then we will display planning failed as before. There's a note here that we have to call trigger after each call to change something render in RViz. So that's why these trigger functions are called here. And all we need to do now is build, run it, enable visualization, and then can enjoy our visualization in the GUI of RViz. So the draw trajectory toolpath will actually publish a message as a marker array. So here it tells us that in RViz we have to add a marker array to actually see it. And that's all it is. So let's give it a go. So as before, I am going to do a build. And I will source it once again. And before we run, let's open up our RViz and set it up. So in this case, our robot is already there. So what I will do first actually is to move it back to this test configuration. So here I'm going to move it to roughly there. And before we plan this, just make sure that you turn off the Cartesian path as well. Otherwise, it will try to go in Cartesian path from here to here, which is, I think, is impossible because that goes through the body of the robot. And we can turn that off as well. So let's see if we can plan for this. Yep, that looks fine. So let's execute it. All right, so now let's add the things that are necessary. So first thing is we're gonna add the marker array. So that we can see the toolpath. It won't come up just yet as a topic. Let's actually go back to the tutorials. What is the topic that it was looking for? Okay, so the topic is called RViz Visual Tools. Let's just copy that and put it into the topic. RViz Visual Tools, and we're gonna add the buttons as well. So panels, add new panel, RViz Visual Tools GUI. So you can see at the bottom here, we have these buttons: next, continue, break, stop. And we're gonna be looking at this next button. Cool, so now everything is set up. Let's just run the code. So we will do ROS to run, hello MoveIt, hello MoveIt. And let's see. All right, so now it says waiting to continue, press next in the RViz Visual Tools GUI windows to plan. So let's do that. I'm gonna hit next. Oh, it's made the plan there. It's a very complicated motion. As you can see, the toolpath and how it ends up there. For now, this looks okay for me. Later on in this video, we'll add some collision objects at the bottom here so that the robot doesn't go through the ground like that, which is typically what we don't want for these robots. But for now, it is okay, so we can hit next to execute. As you can see, there's this text here that we added as well. All right, that's great. And our code finishes cleanly. Now we can run this whole thing again. So when we set the start state to current and the goal state to test configuration, we can move it back to where it was. I'm just going to do plan and execute. And then remember how this toolpath looks like. It's not guaranteed that running the exact same code will give you the same trajectory. Because there might be multiple trajectory that can reach from point A to point B, and the default planners of MoveIt uses optimization, which can give you different results every time. So just by running it again, we can see it pretty clearly. So we hit next now, it should give us different plan. As you can see, this is a completely different plan, even though it ends up at the same and effective pose at the end. And the robot looks different as well. You can see how now, if we have a look at that again. So we can do show trail. It's a bit hard to see, but you can see how at the very end, the robot's now under the ground. So what if we don't want that, right? What if we want our robot to avoid obstacles like the ground or other things in the environment? That's what the next tutorial is for, which is called planning around objects. So let's do that. All right, planning around objects. This tutorial is all about this planning scene interface. So first thing is we need to add it to include. So let's just add it at the top here and change the target pose. Now, for me, I've played around with a few target poses before making this video. So I know what's a good one for the current robot that I'm using, which is the UR3e and the RG2 gripper. So I'm going to put the values here instead of the ones that are recommended on here. This is for the Panda. So here I'm setting it to be 0.707, y to be same. This is pi divided by 2. That should be 0 and w 0. And I'm going to make it go to x equals 1, y equals 3, and z equals 2. 0 0.1, 0 0.3, 0 0.2. And this should make our end vector point downwards at a roughly reachable position. Next thing here is to create a collision object. So let's just copy this entire block here. And this can be anywhere. I'm going to put it right after the set target pose code. Here's our collision object. First, it grabs the planning frame from the move group interface, creates this collision object in that frame, name it box1, and it's using the solid primitive shape, defining it as a box, and with these sizes. I think by default in the tutorial, it's like this wall in front of the Panda. In our case, more relevant to me is to create the ground or whatever surface the robot is mounted on to make sure that the robot doesn't collide with the ground as it moves around. So I'm actually also going to change these values a little bit. So my box would be pretty wide and a square, but relatively thin because it's the surface. So I'm going to make it perhaps even a meter by a meter, but only making it about 10 centimeters thick in Z. Also the pose as well. I want my box to be right directly below the robot. So X and Y can be 0. And since our box is about 10 centimeters thick, if we put it at 5 centimeters Z, it should be right underneath the robot. But I'm also going to leave a little bit of a gap so that the collision detection doesn't always detect the collision between this box and the base link of the robot. So I'm going to make it negative 0.06, for example. So we're leaving this 1 centimeters gap. And we're going to push it into our collision object message and with the operation to add. So what this operation add does is if an object with an ID box1 doesn't exist, it will add that object. But if something named box1 already exists, it will delete and then update it. The next step is to add the object to the planning scene. So here we have constructed the object. Next, we need to add it to the scene. So we're going to do it right after. And here we're going to use this object from this class planning scene interface for MoveIt. And it has this function called apply collision object, which we can add our box. And that should be it. The rest of our code can stay the same. Well, we'll just plan for a trajectory to our pose. Now, actually, before building this, just to show you that there's a difference between having the box object there and not, what I'm going to do is I'm going to comment out this line that applies the object to the planning scene. And I'm going to build this without it, just to see how our original trajectory would look like with our new target pose. So let's have a look at that. So I'm gonna build. I'm gonna source. All right, so let's open up our RViz and let's run our Hello MoveIt node and hit next so that I can plan it. Okay, so we can see here the plan path to our desired goal pose definitely goes under the ground. So if we execute that now, this will be a dangerous motion if a robot is mounted on a table, which typically is. So we definitely need that planning scene in place. So let's add it back in and see the difference. Right, so in the code, I'm just gonna remove the comment for this. And now we're applying the collision object. I am going to build it again. And as it builds, I'm going to return the robot to the test configuration. Right, it has finished building, so I'm going to source and just wait for a robot to return. And now we'll run the Hello MoveIt node again. Now we can see we have this object, the table, underneath the robot. Great. So now we hit next. Oh, great. Okay, so this is the plan I came up with without going to the ground. Let's make a 360 spin. A bit excessive, but our requirements was that it doesn't collide with the ground. So it achieves it. And then we can hit next for it to execute it. Great. So by the end of this tutorial, you can already see how useful this is. So you can start adding objects to your scene. If you know your robot is in this fixed environment, then you can make sure that it will never collide with your environment. And you can visualize your paths before executing it as well. However, what if you want to do something more than that? So what if you want to construct like a pick and place motion? So as you can see, every time we use MoveIt to plan for a motion, the planner will spit out different solutions, right? And if you set up your planning scene with more constraints, maybe the motion will be more predictable, but you can't really rely on that. And for a more longer sequence of tasks, like a pick and place motion, what you want to do is to basically go through a few iterations of planning. So at each step, you want to see as many valid plans as possible. And then you would choose the sequence, typically based on how long it takes for the robot to complete that entire sequence, depending on what plans it picked. So for something like that, MoveIt Task Constructor can be quite useful. So that is our next tutorial, is to construct a pick and place task with the MoveIt Task Constructor. If you want to learn more about what MoveIt Task Constructor is, I highly recommend reading through this concepts page that they have, where they explain in a lot of detail some basic concepts like what are generators, what are propagators, what are connectors, and how these are implemented to construct a sequence of motions, which they call stages, to become a task. Essentially, some of the stages can be independent, but then some of the stages can actually influence the other stages that in time might come before or after it. So this is why something like this can be very useful in achieving a very complex task. But for now, we're only gonna follow through with the tutorial and see if we can actually run it for this pick and place task. So the first thing that it asks you to do is to download MoveIt Task Constructor and then building it yourself. I will not recommend doing it just as before. We're just gonna use the binaries that they provide. So I think the only ones that you really need are, so we can do it sudo apt install ROS humble Jazzy if you're using Jazzy, MoveIt Task Constructor core, which is down here what they recommend that you use. Yeah, I already have done it. If you want to install everything about MoveIt Task Constructor, what you can also do is just to do this, MoveIt Task Constructor dash and then a star to install everything that's related to MoveIt Task Constructor. That's the full list right here. So let me look at this. So you have the core. Oh, you actually don't need these debug symbols one. So you only need MoveIt Task Constructor core, MoveIt Task Constructor messages, capabilities. Probably don't need the demo one as well, because we're doing our own demo. And what else is important? MoveIt Task Constructor visualization. This one is also pretty important. Yeah, you only need those. Later on, we'll add these to our package XML as well, which means you can also use ROS-dep to install it, like we just did for the other packages. If you try to build MoveIt Task Constructor from source, it will take you maybe an hour, or on a fast computer, like 30 minutes, 20 minutes or so. So I don't recommend building it from source. Okay, let's move on. So now we're going to create a new package. So it'll be a different package than our Hello MoveIt one. So I'm going to go to my workspace. I'm already there. I'm going to go to source and I'm going to create this package called MTC tutorial with a node that's also called MTC tutorial. Okay. And what it asks us to do is go to the package.xml and copy and paste that in there. So let's give that a go. As you can see, we've now created this MTC tutorial package. Here's our package.xml. Copy paste that here, and we are depending on this MoveIt Task Constructor core package. And we need to update our CMake list as well. Similarly, so I'm just going to copy this and put it into my CMake list. Pretty straightforward. So we're finding this MoveIt Task Constructor core package is required, and we are setting it as the dependency for this MTC tutorial executable, and then installing it so that we can do like ROS2 run MTC tutorial. Okay, so that should be done. I'm actually going to do a test build, which it doesn't tell you to do in here, but I'm just going to do it anyways. It's a safe thing to see if this actually builds. So we're going to do a Kokan build. But instead of Hello MoveIt, now we are looking at PC tutorial. It's building. All right, so we've successfully built it. Great. Okay, so here's what it asks us to put inside our MTC tutorial CPP. Pretty long script, but it doesn't actually do much. So let's actually copy it in first, and then I'll walk you through what it actually does. So here's our source, here's our CPP. Let's copy that in. Okay. So let's see. So we here are including all of our dependent header files. So it's using the planning scene as before, but we have these task solver stages from the task constructor. We're creating a class called the MTC task, creating a node, and we have these two functions, do the task and setting up the planning scene. Here's our setup planning scene function from within that class. As you can see, it's adding this object in the word frame, and the primitive that's using here is a cylinder. It's different than the box that we used before, and we're putting it at this pose because this is the object that we're gonna be picking and placing. So in this video here, you can sort of see what they expect with the Panda robot, that this cylinder pops up. Now for my robot, as again, I've played around with this a little bit. I know the sort of dimensions and pose that we should go for. So I'm gonna put that here instead of the default values. So I actually want my cylinder to be horizontal to the ground because I want my robot to pick it up like this from the top. So we first gonna probably need to rotate it. So I know that my orientation X is that, so pi over 2, and I want my Y to be 0, my Z to also be 0, and my W to be pi over 2. And then for position, X, this is a bit too far for the UR3e robot, so I'm going to make it 0.3. Y is negative 0.2. And then Z, we want to put it on the table that we have on the ground. So just a slightly bit. So if our cylinder has the radius of 0.02, putting it at 0.02 should make it stay on top of the ground. So that should be our object. Cool. And then we are just putting that into the scene. Here's our do task function, which first create the task. We have a look at that later. But as I mentioned before, a task comprises of many stages. So here we are initializing the task and we are doing planning. So planning for a task means to plan for individual stages and then connecting them together. And here the number 5 basically says that if we cannot come up with at least 5 versions of this task, so 5 different sequences of stages, then we consider task planning failed, because we don't want to just arrive at one possible sequence and then be happy with it, because the whole point is to do multiple planning options and then picking the one that is most suitable. And here we're setting the minimum to be 5, and we consider the task planning as a failure if we cannot come up with at least 5 plans. Here we are just using the first solution, the first solution that we found, and then we're gonna execute that task. So going through the sequence of stages and executing them. Oh, so that's all that is. Here is the actual task. We are calling the task demo task, and here are a few consts that we are using throughout the whole task creation. That can be useful instead of having to just use the name of a robot and stuff repeatedly. We do need to change this though. So again, we're not using the Panda. We are using the UR OnRobot manipulator. Our hand group name. So this is the end effector. In our case, it's called the UR OnRobot grouper. And our hand frame, which is our planning frame. As I mentioned before, this is our we should be planning in this frame if we want to pick up objects there, and we show names here. That's called gripper TCP. So that's what we are using here. Okay. Right, so we are setting these properties for the tasks using the names that we defined. There's some pragma here to disable warning. Current, which is just the current state of a robot, can be a stage. So this is what we are doing here. We're adding the current state as a stage in our task. Here we are defining a few planners. So planners are the ones that actually will plan for individual stages. So we have the sampling one, which is what we have actually been using so far to plan for motion of the manipulator. So it actually samples a bunch of randomized configurations of the robot to connect from one configuration to the other. We have the interpolation planner, which is probably the simplest one, which is just a solver for interpolating between configuration A and B. And then Cartesian planner, which is what we've seen before, where we want something like the n effector to move in the Cartesian path. Right, so we have a few velocity scaling factor and acceleration scaling factor. So by default, it's 1.0, but I'm actually going to lower it down, something like a bit safer, like 0.5. Especially if you want to go to a real robot, then you probably don't want to immediately go at its maximum speed and acceleration. And apart from the current stage, only other stage at this stage is this open hand stage. I just said stage too many times. All that this stage is doing is to use the interpolation planner to open the gripper. Right? So whatever state the gripper is at the moment can be closed. After it goes through this stage, it should be opened. And we do that by setting the goal for the hand group to be opened. Now, this goal is actually, it should be defined in the SRDF. So let's have a look at that in our robot. So in our MoveIt config, and I think by default in this tutorial, this is using the Panda, and they have this defined in the Panda's SRDF. For your OnRobot MoveIt config, you can look at the SRDF here, and you can see that there's a few groups, group state that we've defined. We've used a few for the ARM before, like this test configuration to make it go to a natural configuration. And here are closed and opened. As you can see, opening for the gripper means going to 0.1 for the finger width, and then close is setting it to be 0. Right. This stage should make the gripper go to the opened state, which is the 0.1 meters. And that's it for our task. Our tasks only have 2 stages at the moment: current and then open hand. That's all it is. And then this will return this task. And then this create task function is used inside this do task function, which is creating the task and then checking if we found 5 solutions. If yes, then we'll execute. And here is our nodes. It has this multi-threaded executor and a bunch of functions here that we need to use to spin up the MTC task node. Set up the planning scene. So that should add our object and then doing the task. That's all that it is. Okay, so let's build and see what we can do. All right. So I'm going to build this. Awesome. I'm gonna source it. And let's open up our RViz. Okay. Actually, I forgot something. So if we scroll down past all the definition here, we can see that they actually build a launch file, because you need to pass the MoveIt config. So in this case, it's using the MoveIt config for Panda, and then passing it to the demo node. At the moment, we don't need it because the only planner that we're using is the interpolation planner, and that works without needing a MoveIt config. But later on, we do need to create a similar launch file, so that MTC actually gets the right kinematics solvers, and the robot description model and the SRDF, just called the semantics model. Here, it also walks us through how to set up the RViz configuration, which is what we're going to do now. So we'll need to add this MoveIt Task Constructor visualization, and then we need to display the solution in the motion planning task. So let's do that with RViz first. So it's our RViz, what we had before. So what we need to do is we need to add a panel. So we go to panels, add new panel, and we want this motion planning task inside MoveIt Task Constructor visualizations. So here's our motion planning task at the bottom. I'm just going to drag it to the right, actually. Let's put it nice here. And then we'll also need to add it to our displays here. So we're going to add the motion planning task into here. You can see there's an error at the moment, which we haven't set the topic yet. So to go to task solution topic, and I think the tutorial asks us to make it /solution. So let's do that. Cool, very nice. And you can see that this pops up. Okay, so we'll have a look at those tasks later. Okay, just making it a little bit wider. Now we should be good to go. So instead of a launch file, I'm just gonna run it. So ROS2 run MTC tutorial. So this should add our object. So here's our cylinder laying horizontally on top of the ground. Actually, the ground was added from our previous tutorial. Like at the moment in our code, it doesn't have it yet. And we can see the tasks that are created here. So we have the current stage of the robot, which is sort of like that, and then an open hand. So if we click on it, you can see the solution that it found. So in our case, our gripper is already opened, so that's why it is not doing anything. But if we go back to our motion planner, and let's just close it first, and we'll run this again. So let's just set this to current, and I'm just gonna close the gripper. Set to close. Yep, so closing the gripper there. And I'm going to turn off my motion planning interface as well, so we only see the motion planning task one. And if we delete this task, and then we'll run it again. Actually, I'm gonna turn off the marker array as well. We should see this task, which opens the gripper. There you go. So now our task opens the gripper because currently is closed. Open hand. There you go. That's our task. That's it. And we should have executed it as well. As you can see here, it actually executed it. All right, now let's actually go through with the rest of this and add more stages to our pick and place task. As you can see here, these are the steps. So we have the current state, we'll open the hand, we move to a pick position, we pick up the object, which includes smaller stages like approaching the object, grabs being allowing contact so that it doesn't trigger the collision check between the gripper and the object, closes the hand, attach the object to the hand, lift it up, move to the place location, and then going through the place stages. So doing IK to find out where to place the object, opening the gripper, detaching the object, and then retreating from the object, and then going back to home. Okay, so I'm going to turn this off. I'm going back to the code. So right now we only have the open hand stage. Yeah. So we're going to continue adding to this task. The first is the pick stage. So let's copy that in. Right. So this is just called move to pick. So this will use our arm group and the sampling planner. So this is going to before attempting to pick it up, setting it into position to be ready for that. Okay, so just following through here, we're going to create this pointer, and now we are adding the graph stage, and here we will need this serial container. So that's a container that can be added to a task, can host several substages, right? Because graph being can like picking up an object, it requires several stages within it as well. So that's what this is. I'm just gonna copy through. This is called serial container called pick object. So next we have this move relative stage, and move relative is actually a stage that uses the Cartesian planner. So this is when we want to actually approach the object. We don't want to go around it, make any curve movement. We're going to go in Cartesian space directly towards it. So here we're going to add that. So make sure that this is within the scope of this graph's pick object serial container. Okay, so we don't want to close the scope yet. So I'm going to paste that here. Right, so this is a move relative stage called approach object. The link is our hand frame, which is that gripper TCP frame, and the hand forward direction, the default one's already correct. The robot that we use also have the Z vector as forward, so that's okay. Now we need to perform inverse kinematics to find the graph pose. So here we're using the stage called generate graph pose. Again, I'm gonna copy it here, and you can see actually we'll be sampling a few possible graph poses around our object. Because our object is a cylinder, what's happening here is generating poses, and that's set by this set angle delta function, which is pi divided by 12. So that's 180 degrees divided by 12, which is 15 degrees. So all it does is from around our objects, we're gonna solve for different inverse kinematics solutions for poses that are around 15 degrees each around our cylinder to have a bunch of options to how we want to pick up this object. So continue with the map here to generate the pose. We're using eigen to calculate the poses. In the example with the Panda robot, they do have this translation that is added to the graph frame transform. But for our case, because our graph frame is already the gripper TCP, which is already where we want to pick up the objects from using the N effector, we don't really need this, right? So we just grasping where gripper TCP is. So I'm just gonna get rid of this translation. And now we're gonna continue and compute IK. and finishing this stage. Cool. So this is a stage called Compute IK, and Graspos IK is what we're gonna call it. There's a few parameters we can set here, like the maximum IK solutions, which is 8, which is fine. It might take a bit of time to go through all the IK solutions for a single possible pulse. And remember that we're going through this like 15 degrees at a time. I might lower this for now, maybe set it to 4. This is the mean solution distance, so that the solution needs to be different enough for we to accept it as a valid possible solution. We don't want many solutions, but they are too similar to each other. And yeah, now we're adding this, we're inserting it into the graphs serialization. Okay, cool. The next stage is this stage that's called the modify planning scene stage. So this is where we can allow collision so that the planning scene doesn't trigger a collision between the gripper and the objects. Right? So during grasping, we want to allow the collision, but during any of the other stages, say like after we've done the place motion, then we want to make sure that it doesn't actually collide with the object. So here we're going to add that stage called modify planning scene stage. And we're going to allow collision between the hand and the object, and then inserting it into the grab stage. Okay, let's move on. So the next one is now that we've allowed collision, we can actually close the gripper or close the hand in this case. So this is a simple stage using just the move to stage with the interpolation panel. You can see here, similar to the opening that we did before, but we want to go to close. So our robot is actually configured with the closed state is closed with a D. So we need to make sure that's what we write here and not just closed like the Panda. Keep going. So now we can use the modify planning scene again, but to attach the object to the hand. So after this attachment, when our robot moves around, the object will automatically update its pose fixed to the hand frame. So let's do that. Cool. So this stage is called modify planning scene again, and we're just using its attach object function. And now we can lift it up. So by lifting it up, we are using the move relative stage here. Let's copy it in. With this, we are actually using this very useful function called min-max distance. So the solutions that it gives us, as long as it's within this range, should be considered valid. Now, by default, it's lifting it up by from 10 centimeters to 30 centimeters, which can be a bit too much, I think, for our application, because you risk calculating solutions that are like out of reach of the robot. So we're gonna do a simple one, maybe like lifting it up by 5 centimeters all the way to maybe 15 is good enough for us. Maybe 20 for lifting up the object from the ground. Okay, and we are doing it in this upward direction, which is relative to the word frame. So the direction is Z inward and inserting it into the graphs. And that is all the stages that we need to pick up an object. So we can end the task. Instead of continuing, let's just see how it works using this current configuration. So I'm just gonna go build and see what it does. All right, so let's build it. All right, so it's finished. This is the warning. Now, before we can actually run this, as I mentioned before, we will need a launch file. So by default, I think they have given us this launch file here, which we can use as a starting point, but this won't be enough because here they already have this MoveIt resources Panda package that will give it the right MoveIt config resources. But since with our OnRobot package, we are constructing the robot description and semantics description every time we launch it, we have to do it a little bit differently. So we have to write a launch file. Let's do that. Okay, so in this MTC tutorial folder, I'm going to create a new folder. It's called launch, and I'm going to create a new file. Let's call it MTC demo.launch.py. Copy it here for now, and let's just make sure that we installed it in our CMake list as well. Cool. So this should put our launch files into the shared directory, which then we can use. The parameters that we need to feed into our nodes would be the robot description, so it gets the model of the robot semantics description, so it can get like the different groups and the states that we defined, the kinematics description, so it knows which IK solver to use, and other things like the planning pipelines, so that I can use for the sampling or Cartesian planning solutions. And these are the things that we can get from our MoveIt config. So in our MoveIt config launch file, you can see here, this is what we launch to start our MoveIt and RViz. And here is how the description is built based on the UR type and the OnRobot type. Similarly, here's the semantic description and all the planning parameters as well. So I already have it here. I'm just going to copy and paste it in. I'm going to walk you through it. Okay, so this is a copy from that. So here we have, firstly, this is in Python. So we are importing a bunch of launch description, constructing classes that we can use. So the UR type, the OnRobot types would be are important in our configuration, as well as these safety limits and margin and positions required by the UR robot specifically. Join limits, physical parameters, visual parameters, and here we build the robot description, build the URDF essentially from those parameters. And here's the semantic, the SRDF, and here's the configuration for the open motion planner library, the OMPL, which will be used for our sampling planners. And these are the parameters. I'm just going to group them into here and put that into the node. Right, so change the name should be MTC tutorial, and this should be called the MTC tutorial package. Okay, so with all that set up, we can now try to build and then launch it. So let's give that a go. Build it. Cool. And then source. And now we should have that launch file. So launch MTC tutorial, we call MTC demo.launch. So let's open up our task constructor RViz and delete the old task. All right, so let's give this a go. I'm gonna hide this as well. See if this works. All right, it is going, and it has successfully picked up the object. That was fast. All right, so here's our entire task like that we just built. As we see, we have the current state, open hand that we started with. this move to pick one with all possibility here. But as you can see from the from the arrows here as well, the arrows that go both ways are generator stages, and you can see it actually all starts from this grasp pose, which is the most important step in this whole task at the moment. And you can see it try to generate like a bunch of these. I mean, how many of these did it try? 32 attempts. Some of them are impossible. For example, that one where it tries to pick it from the side, and you can see it collides with the ground that we set, that we added to the scene previously. So that's why it failed. Similar to the other ones here, I assume. Yeah, all the ones are on the ground failed. I'm gonna sort it by cost. The one that succeeds, this one succeeds. Yeah, it's a weird configuration. Some of these other ones are the ones that are above the ground, which is why they succeeded. Yeah. So the robot basically goes through all possible configurations to and solve for IK to attempt picking, and this solution will actually propagates into the past. Right? So depending on the grasp pose, it will determine how to approach the object. From the grasp pose solution, it will generate this approach object, which is this distance away from the object that we defined. And then you can see this arrow goes up. So from this motion, it will decide this move to pick motion, which is when it gets from its original or the current state to the beginning of that. So at the top of this, approach object motion, right? You can see how this graspable IK propagates the planning backwards in time. And similarly, this will go forward. So here we close the hand. Yeah, different ways. And see each of these closed hand motion is depending on the valid IK solutions as well. And then based on each of these, that will propagate to how it can lift it up. There you go. And when you add all the costs together, we have the total cost for the entire task, which comprises of all of these stages. Go here, go down, pick it up. There you go. Here's another option. Yeah. It's like Doctor Strange in Avengers Infinity War, going through 14 million possibility. And like, how many did we pick up the object? One, or in this case, two. Okay, anyways, we can continue. So I'm gonna stop this. And let's just continue with our code. So we've done picking up. Now we're just gonna add placing stages, which is gonna be very similar. So let's copy this move to place. So now we pick up the object, now we're going to move to place. And you can see the placing stage will propagates to this one as well. So let's do this. Move to place. Here's a bit of a thing that I will need to change. So for whatever reason in the tutorial, the group planner for this also involves a sampling planner for the hand, which is not necessary. Like during this move to place stage, we're not moving the hand, just gripping the object. So we can just remove it here. There you go. And here's our placing one. So similar as before, we're opening up this scope and creating this serial container. So serial container is that. Like this pick object one is a serial container. Now we have a place object serial container. Yep. And here we do the same thing. We're computing IK and we're going to sample a few possible placing poses. So let's add that in. Okay. So here, as you can see, we are generating place poses with the object. And interestingly, for the place pose, we are defining it using the frame ID object. So basically, we are defining a pose that's relative to where the object originally started. So this is a relative motion because we set the frame ID to be object. So in the example, they're moving it in the Y position of the object. But since our cylinder is now on the side, its Z is actually the direction we actually want to move in, because I want to pick up this object and then perhaps move it like over here and then place it down. So it should be in the Z direction of this object, not the Y. So let's change that to Z. So we're going to move it 0.5 is okay, but we actually do need to make it negative 0.5 because I think the positive 0.5 will make the robot try to place the object sort of over here, which is definitely outside of its reach. So we're actually going to go negative 0.5, which is somewhere over here. We can keep the orientation the same, setting the pose. Yep, and here is where we hook into the attach object stage pointer that we defined at the very top here. And the reasons for this is that, remember the scopes where we are doing for these stages, if we didn't have this no pointer to connect the two, then this will be invalid. This will be created inside the scope, which will get deleted when we go out of it. So this is why we needed a pointer. And here we're computing IK to solve for how we can place it. For placing, for some reason, they're setting the IK solution to 2, which is fine. Similar parameters as what we had before. Okay, so same thing. Now, when we're ready to place the object, we will open the hand. Yep, so open hand, go to the open goal, which is already correct. Next, we need to, so after opening the hand, we can re-enable collision. So now we actually do check for collision with the objects. Because we don't want to release, like placing the object and then immediately do a motion that, whacked it out of place or hit it or something, right? So we definitely need to forbid collision, and then we can call detach object using a modify planning scene stage, kind of the inverse of what we just did before. And now we are retreating instead of approaching for the object. Now we are retreating. Use this next step here. So this is also a move relative motion, and we're calling it retreat. In the hand frame IK, same min max distance before. I'm also gonna reduce this a little bit. Yeah, maybe just like 5 centimeters to 20 centimeters of retreat is fine. Within that range, I think is good enough. We are retreating in this example in the word frame, and here they're making it go to negative relatively in the X direction. But for our case, because we are placing the cylinder horizontally, we can just retreat upwards. I think it's okay. So we can just set it to be Z of 0.1 is good enough. Okay, and now we just end our zero container and add it to our task. And we are ending it with this final stage, which is move to home. Right. And then for returning home, here in the example code, it makes the robot go to this ready state. We do not have a ready state. What we have is this test configuration state that we've been using. So we're going to use that instead. So test configuration. And that is the end of our task. So let's give this a go. I'm very excited to see it doing this entire task that we just constructed. Okay, so I am going to build this. All right, and I'm going to source it and ready to go. So let's delete this demo task and let's visualize a new task. You can see it's going through all the planning stages here. Hasn't come up with any full solution yet. So yeah, like you can see we've added this move to place and place object into our task. Just calculating. Oh, it failed. Okay. Okay, so that failed, but it's a good point to try to debug why it failed using this information here, which is a reflection of the same information that's in RViz. So here's our top level demo task, which actually failed. There's 0 solutions. Here's are the solutions I found for each of the stages. So all of them looks like there's some solution, but let's see here. Yeah. So here in the grasshopper IK, it found 21 solution, but it wasn't able to propagate anything back to this approach object stage. Okay, and then similarly, so this is supposed to propagates forward, but it didn't manage to propagate any of the solution forward. And then that sort of like cascaded into our flow here up until this lift object solution. Yeah, the rest looks okay. So it's 2 solutions, 6 solution, place object here. Also couldn't pass any of these solution forward to the place ball. So our IK stages are the one that are problematic. So let's queue this and let's see if we can fix that. I think what we need to do is just to let it generate more solutions. Yeah, so max IK solutions is 4. Yeah, that may be my mistake. Set it to be 8, like what we had before. It take more time. Same with down here. It may take more time to solve, but it might be needed to come up with actual solutions that are not in collision. So let's build it again and then run it again. Okay, so now let's run this again and see. All right, so it's going through the different solutions now. Let's place our objects there. Let's look at the IK. So it's come up with a few IK solutions. It's more promising. It's propagating through the other ones. It's problematic that all the move to pick ones are failing. This is the one that's problematic at the moment. So whatever solutions that these pick objects ones are producing, the bot cannot move to them. And the comments are all timed out. So it might just be such a big motion from here to here that the sampling planners that it's using to get this very simple like move to pick motion to fail. Let's fix that too. And give it a bit more time to plan for this motion. I'm going to stop this and then fix that in the code. Right, so that should be the sampling planners that we use. So that should be our move to pick. Planning timeout is 5 seconds at the moment. So let's let it plan for maybe 15 seconds. Take a bit more time, but at least it will succeed. Similar to this one. Yeah. So move to place. I'm gonna make it 15 seconds for all the move to planning. So let's delete this again. Let's build and try again. All right, let's give this a go. Oh, nice. So see, the move to pick one has found a solution. Move to place is still failing, even though we set it to be 15 seconds as well. So let's that it will continue. Oh, it's found another solution. Okay, nice. There we go. Now that we have more solutions for these, now we have 2 valid demo solutions. Let's have a look. This one does that. Very nice. This is the second solution. Now, I think because we still set the task plan to come up with 5 solutions before execution, this might take a while. So one of the things that's very telling here is that it found only 6 different ways to pick up the object, whereas it found 49 different ways to place the object. So that tells us that we can change the way that we're generating the grabs poses for picking, or maybe relax some of those constraints or do something else to get better results. Yeah, so out of the 12 solutions that it found for grasping, it was only able to generate 6 different approaches, whereas in place, it actually found 120 ways to place the object. So it's a magnitude of 10. So the way that we're generating the grabs poses by rotating it around the z-axis might not be the best way. With dot cylinder, what we can also do is generating more grabs poses along this z-axis, or maybe computing in lower resolutions as well. Like instead of 15 degrees at a time, we can do it at like 5 degrees at a time, for example. So let's implement those changes and try this one last time. All right, so let's have a look at the code for our graphing planning. Here what we can try is to make this a bit bigger. So let's do it at about 5 degrees at a time. So that would be dividing it by 36. Yep, 5 degrees variations. And we will lower the resolutions, otherwise it will take too long to plan. So max IK solution should like maybe be 3. And we can keep the placing the same, because I feel like the placing, it's already nailed that. Okay, so let's see if this will improve the number of solutions that we get. We build, and we source, and we run. Oh yeah, that's much better. Immediately it's found a pretty good solution to pick up this object and move it around. So the whole planning took 1.36 seconds. This time it came up with 5 very nice solutions here. Here's 1. Here's 2. Another one. Okay, flip it around this time. It's I'm guessing a similar one. Yep. And so I think it went with this one, which is the most optimal. Well, there you go. That's MoveIt Task Constructor and how to debug it if you run into issues like I did. So that's the end of this video. Thank you for watching, and all the links to the packages that I used, as well as the code that we've written today, will be made available in the description below. I hope you found the video useful, and good luck on your robotics journey.